Good morning, everyone. Thank you for joining us today for a free Water Environment Association of Texas webinar. We have a terrific group of panelists with us today to discuss peracetic acid for disinfection of municipal wastewater effluent. So now I'd like to present today's panelists. Our first presenter will be Dr. Carl Linden. Dr. Linden is a professor of environmental engineering and the Mortensen Professor in Sustainable Development at the University of Colorado Boulder. He has a BS from Cornell University in agricultural and biological engineering and an MS and PhD from University of California, Davis in environmental engineering. Dr. Linden's research investigates the efficacy of UV and oxidant disinfection for inactivation of pathogens and the use of advanced oxidation processes for the degradation of organic and other emerging contaminants in water and wastewater. Dr. Linden is a consultant to the World Health Organization for revising the guidelines for drinking water quality and a member of the WHO Water Quality Technical Advisory Group. He received the 2013 Pioneer Award in Disinfection and Public Health from the Water Environment Federation and was Water Reuse Association's 2014 Water Reuse Person of the Year. Our second presenter is Dr. LRWRA da Silva of Stantec. Dr. da Silva is Stantec's Rocky Mountain Region Water Reuse Practice Leader. LRWRA conducts water and wastewater treatment technology evaluations, feasibility studies, and implementation. She is also heavily involved in policy development at the state and federal level. LRWRA currently serves as the Secretary of Water Reuse Colorado and on the Water Reuse Issue Area Team for the Water Environment and Reuse Foundation. As a moderator, I have the pleasure of introducing myself as the third speaker. My name is Dr. Michael Watts. I am a water technology leader and an engineer with Garver in Dallas, Texas. For the past 13 years, I've had the pleasure of focusing on improving the design of oxidation and disinfection processes for water reclamation. In recent years, as you'll hear about later in the presentation, I've had the opportunity to lead studies of PAA disinfection on the laboratory bench and at pilot and full scale. In addition, I have assisted in the development of criteria for effective PAA disinfection and safe PAA residual discharge. Our final presentation will be from Sarah Stewart and Leonard Levine. Sarah Stewart is an environmental engineer with 15 years of experience with planning and design for both water and wastewater utilities, site civil design, wastewater collection systems and treatment, as well as water and wastewater pump stations. She's an employee with CDM Smith for the past 10 years, serving in multiple roles, and is currently an associate and senior project manager. Joining Sarah will be Leonard Levine. Leonard is a licensed professional engineer with over 40 years of experience in design and operation of industrial and municipal wastewater treatment facilities, including the development and implementation of operator training programs for wastewater operations. Currently, he serves as technical director for Gulf Coast Waste Disposal Authority, which you'll see on the presentation today referred to as GCA, where he's responsible for the oversight of technology selection, design, and operation for all GCA facilities. Leonard has been employed by GCA since 1980. Prior to his career at GCA, he was a consultant who did process design and operational upgrade work in a variety of wastewater treatment sectors. So I will, with our speaker introductions, I will go ahead and turn this over to Dr. Linden, who will be discussing peracetic acid fundamentals.
Thank you. Thank you, Mike. Welcome, everybody. I'm here to talk to you about some fundamentals of peracetic acid disinfection. And the outline of my presentation will follow first some chemistry and composition of PAA, talk about some indicator organism inactivation, some issues around residuals with PAA and effluent quality. We'll talk about some toxicity results that have been presented on PAA in natural systems, and then look at compatibility of PAA across a wastewater treatment system and some of the benefits of PAA. So there's a number of major classes of disinfectants that can be used for wastewater treatment. We have the halogen ones, which you're very familiar with: chlorine, hypochlorous acid, hypochlorite. Then there's the peroxygens, which include hydrogen peroxide and peracetic acid, as well as ozone. Then there's the physical disinfectants, such as UV light, UV disinfection. So we're going to be talking about the peroxygens here, and PAA in specific. Wastewater treatment at the national scale across the United States is certainly dominated by chlorination, although we've seen the rise of UV disinfection. About a quarter of the wastewater treatment plants are using UV as a disinfectant, and a very few are using ozone. You can see the market is still dominated by the halogen-based chlorine disinfectants. So with very limited market share available at this point, why is there a lot of talk and interest in PAA? Well, there's a number of reasons here. Compared to the halogens, it's certainly inherently safer. It's used as a surface disinfectant in many settings, and it can be used for disinfecting many different types of applications in addition to water. It's also very stable when it's in a bulk solution. That stability is predicated on a very pure solution of PAA, but once it's in a pure solution in its container, it can stay stable for a long amount of time. It's fairly quick to retrofit a system with PAA disinfection if you already have something like chlorine. And then, of course, there's no byproducts formed from PAA like there are with the halogens, such as chlorine. So no trihalomethanes and haloacetic acids to worry about. PAA is an interesting mixture of a number of chemicals. It's hydrogen peroxide and acetic acid. And you get this PAA molecule here. And this PAA is actually in equilibrium with the residual peroxide and residual acetic acid. Typically, you see about 15% PAA in these mixtures, with about 7 to 10% acetic acid and about 20% or higher hydrogen peroxide. And you can get up to 22% PAA in your PAA disinfectant, but remember, it's going to be a combination of these three chemicals: acetic acid, hydrogen peroxide, and PAA. And we're interested in PAA because it's the most effective disinfectant of these three chemicals, and it's the active ingredient that we're looking at. PAA itself is a colorless liquid, and at low pH, it stays as liquid and it's colorless and it has an odor. It's most frequently used as a surface disinfectant. It's very effective for disinfecting bacteria in medical settings and in food and industry settings. So it's not very hazardous, but it does effectively disinfect surfaces when it's used in that application. As far as PAA stability goes, this graph shows the pounds per gallon of PAA in a typical 15% solution here against the months of storage. You can see over more than 12 months, we see a very small loss of strength of PAA, indicating you can store this for a long time. But this is very predicated on the fact that there's very few impurities, such as metals and other reducing agents, in that solution to keep it stable. If you do have impurities, PAA will decay over time, and you'll see less and less over time in your storage container. When you spike PAA into wastewater, there's typically very low demand. With other oxidants like ozone or chlorine, we typically see the initial spiking concentration might go down quite quickly in the first minute or so. With PAA, it's very stable, and you only see a small residual decline, and then a very stable residual over time. And here's contact time between 0 and 12 minutes on the x-axis, and the residual of PAA in milligrams per liter in a number of different tests. And you can see a very small decay from the initial demand of the wastewater. So PAA is very stable in solution. It will last a long time and provide a residual to achieve disinfection of indicator organisms and pathogens. This graph shows the effectiveness of PAA as a biocide for E. coli. On the x-axis here, we have the CT of PAA, which is the milligrams per liter times the minutes of contact time. And on the y-axis here, we have the log reduction of E. coli. And you'll see a nice linear relationship between the increase in CT for PAA and the reduction of E. coli. And typically, we're looking at a goal of about 2 log reduction of E. coli to meet some of the regulations. For instance, the regulation of 126 CFUs in Texas would typically require about a 2 log disinfection of E. coli to meet that, that regulation. And that can be achieved within 20 to 30 minutes of contact time if you have a final 1 milligram per liter residual of peracetic acid. This is all based on batch reactor trials in tertiary effluent. A 2016 study looking at enterococci as well as fecal coliform showed that PAA is slightly less effective for enterococci compared to fecal coliform. This graph shows both chlorine on the left and PAA on the right, and fecal coliform is in blue, and enterococcus is in red. And this is the average CT value on the y-axis for compliance, for meeting compliance for regulatory standards. So you can see in this plot here is that PAA requires a much lower CT for compliance of fecal coliform, whereas the CT required for enterococcus is a bit higher, indicating it's less effective for enterococcus compared to fecal coliform. You see the opposite relationship with chlorine, where it's a little bit harder to disinfect fecal coliform than it is to disinfect enterococcus. When you add PAA to a wastewater, you're going to also add some organic material, which increases the BOD of the water. So that's going to be a factor of PAA addition. And this plot shows on the y-axis milligrams per liter of PAA, and this is all in secondary effluent. What you have here is the initial PAA dose in blue. You have the BOD starting of the water, and then when you add those two together, you get a higher BOD in the effluent. Typically, PAA adds about 1 part per million of BOD per part per million of PAA, but it can also be slightly higher. In this case, it is slightly higher than the 1-to-1 relationship. But in general, you can expect about a 1 milligram per liter increase in BOD per milligram per liter addition of PAA. There have been some studies on the impact of PAA residual on receiving water bodies relating to potential toxicity of the disinfectant going into a natural water body. This slide shows some studies that were done looking at effluent from a water resource recovery facility and PAA about 15% in that effluent. And then dilution studies where we're looking at the toxicity to this water flea, Cerodaphnia dubia, and then the fathead minnow. And these experiments show dilutions of 0, so in other words, no wastewater, 31% of the wastewater, 41% of the wastewater, up to 98% wastewater concentration in these serial dilutions. What the data show relating to toxicity is that when you have about 31% wastewater in the dilution, and you have this Cerodaphnia, for instance, this water flea, you don't see any effect up to 31% of wastewater. Once you get higher than that, though, for instance, at 41%, which is our next step up, we do see an observed effect on these water fleas relating to toxicity of the PAA. So we do see some toxicity of PAA against this Cerodaphnia dubia. And it also impacts reproduction as well. And that reproduction effect was seen at a concentration of, dilution percentage of 31% of wastewater. And that equivalents to about, if you had 1 milligram per liter PAA and you put in 31% of wastewater, you'd have about 0.3 milligrams per liter PAA affecting this toxicity impact. So we do see some impacts on this water flea. When we look at these larger fish, these fathead minnows, we don't see much toxicity. We can have up to 98% wastewater concentration, and we still see no effect on survival or growth. So the results relating to toxicity are somewhat contradictory. They show slight toxicity, perhaps, to some smaller organisms, but not much on larger organisms. So obviously, a little bit more work needs to get done here to understand this, but there could be potential toxicity if you have a residual going in to the water body. So what this means is when you have discharge to a wastewater-dominated stream, you're going to likely want to quench your PAA, and you can do that typically like you do with chlorine. You can quench it with sodium bisulfite, for instance. So in cases where you are discharging to a wastewater-dominated stream, where you're going to have high concentrations of wastewater in that stream, for instance, higher than 31% perhaps, we're going to need to see some quenching of that PAA to make sure we have little to no toxicity impact on that receiving water body. If you're going to be surface spreading or infiltrating the water, the need to quench PAA will be less likely. So with that, I think I'll turn it over to our next speaker, which is LRWRA da Silva. Okay. Okay, there you go, LRWRA. Thank you.
Allegra, if you want to pause for just a moment while we correct the sound issue.
Hello, this is Allegra.
Allegra, is that you?
Yes, this is Allegra. Can you hear me now?
Great. Yes, we've got you.
Okay.
Continue.
Sorry, everybody. Thanks for your patience. Okay, so we'll go back to where I was. Switch the setting here. I apologize, everyone, for that delay. So as Carl mentioned, there's a number of drivers for PAA, and one that I'd like just to underscore is the low capital cost for retrofitting chlorine because you can use existing contact basins. And it's in terms of operation and maintenance cost, ongoing costs, we may not require quenching depending on how tightly you dose to some of those effluent requirements that Carl mentioned. So it is possible to use PAA without quenching. It's all site specific in terms of whether that is feasible or not. And it's overall cheaper than conversion to UV on a capital cost basis. The other thing that we've seen is that PAA can be cost effective for very difficult to treat wastewaters with low UV transmittance, for example. And the typical path to PAA for a utility interested in exploring whether it could be a useful conversion is to do bench testing, then pilot testing, and a full-scale trial prior to looking at potential changes in a permit and installation. In Texas, see if I can advance the screen here. Okay, we've had a number of facilities that have piloted PAA. You can see here many of you all are on that list. And Trinity River Authority has done a full-scale trial. And we'll hear later the case study of the Gulf Coast Waste Disposal Authority that has installed and started up PAA. So if we're weighing the chemical cost aspects of those ongoing costs of PAA compared to, for example, a sodium hypochlorite system. In a sodium hypochlorite system, you may be using ammonia for chloraminating and a quenching agent. In the case of PAA, you dose with PAA and may or may not need a quenching agent. So those are factors in evaluating the overall chemical cost. So how do we determine how much cost we'd have? Well, the bench, pilot, and full-scale trials will give a sense of what dose would be required to be able to meet permit compliance, and then to understand what quenching requirement we might have. That, again, would be site-specific based on how the water responds to PAA, so what residual you might end up with after achieving compliance, but also dilution factors of the receiving water body. And so let's look at what allowable residuals have been put on the product labels for the 5 different PAA products that are approved by EPA for wastewater disinfection. The allowable application rates range from 0.5 to 15 parts per million or milligrams per liter, and all of them are rated to have an allowable residual of less than 1 milligram per liter. One of the products has a special clause allowing for higher residual discharge if the dilution factor of the receiving water body is greater than 12, so very high dilution factor water bodies. But in general, they're rated for 1 milligram per liter or less. And as Carl mentioned,
my apologies. It seems like your slides aren't forwarding. So
okay.
Hold on 1 second while we unravel this, okay?
Sure.
Thank you.
There we go. Okay to proceed? Please start on slide 8. Okay, okay. I'm unclear, Julie, if I should continue or if...
Yep, it looks like we see your slides now. You are on slide 8. So continue. Thank you so much.
Okay, so what would go in a, I think I was on this slide is showing the different products. Just to show, these are 5 approved products for wastewater disinfection. They all are, their label allows for a residual of 1 milligram per liter, though sometimes utilities do go down to lower residual levels for discharge. So in a permit, we'd see that residual limit listed along with pH and BOD, CBOD, or COD requirements, as Carl mentioned, and also a requirement for wet testing like you would have for other chlorine-based disinfectants. So let's look at how this is handled in Texas. The Texas Administrative Code does allow for novel or innovative disinfection processes other than one specifically allowed, and those must be flow-paced and must use chemicals approved by the manufacturer for the purpose of wastewater disinfection. And so as I showed with the product labels on the prior slide, PAA is indeed approved for wastewater disinfection, so it's something that certainly TCEQ can consider. The process by which a utility would work with TCEQ to get PAA approved is the following. Starts with an application for an innovative technology, which includes an administrative review by TCEQ, and they publish a notice of receipt of application and intent to obtain permit after they've deemed that the application is administratively complete. Then they enter a technical review process, and in that process, the staff will draft a draft permit and a technical summary or fact sheet for the application and public notice, and publish a notice of application and preliminary decision. After that stage, the applicant can then review and comment on the TCEQ draft permit and invite public comment. After the public comment period, TCEQ would then publish the final action on the application, which serves as a permit, and then the applicant would go into the normal engineering review process, submitting plans and specs and a summary transmittal letter, and that stage is quite straightforward. TCEQ hasn't yet received a permit change application for a municipal disinfection scenario, and we'll hear later the case of Gulf Coast Waste Authority, their experience with PAA in Texas, but it is an industrial discharge permit rather than a municipal. So let's look at what other states have permitted for that allowable residual. Several states have permitted 1 milligram per liter, and some have gone up to 2 milligrams per liter where there's a very high dilution factor in the receiving water body. Other states have gone down to 0.3 or 0.4 for some of the reasons that Carl pointed out. So it does range depending on the local conditions. Many states, while they have been able to permit PAA, have nonetheless faced some challenges in permitting, and they're essentially around how to handle the residual, given that there isn't a ambient water quality criteria set by EPA for PAA specifically. So they're all looking at residual individually and deciding how to handle that for the state. And there's also a challenge that some states require that disinfection monitoring technologies are done with an approved method that is listed in the Code of Federal Register, so officially an EPA-approved method. And right now there isn't an officially EPA-approved method for PAA measurement, although there are commercially available methods, kits, and probes that do measure PAA. So with these challenges, we're attempting to move the conversation forward with the research project that I'll describe shortly, but the EPA also is engaged in working with states by providing technical assistance to individual regions, through the regions, but also through a headquarters-based Office of Science and Technology technical assessment report that is coming out shortly within the next 6 months or so, and it includes a literature review of PAA and full-scale experiences, implementation strategies, and the performance of the technology as a whole, some basic information on capital and O&M costs, and lesson learned from various case studies. That draft is in review right now and has been coordinated with the ongoing Water, Environment, and Reuse Foundation LIFT project that many of you are involved in, I believe, and I'll give a little more detail on that research project next. Water Environment Foundation is also, Water Environment Federation is also producing a PAA guidance document this next year that will also help push this forward as an option for utilities. Now moving to look briefly at this research project that's hoping to answer some of the gaps in knowledge that we have. The project is a wonderful collaboration among 24 utilities listed in yellow at the bottom, of which many of you are part of the collaboration from Texas. It also involves university researchers and regulatory advisors and partners from the PA chemical providers, as well as Xylem, Whitco, and University of Illinois Urbana-Champaign. Matt Jalbert has provided quite a bit of leadership too in guiding the Upper Trinity Basin Water Quality Compact's involvement in this project, so we're really grateful to Matt, as well as to the project steering committee and project manager through WRRF. In this project, we are documenting the current state of knowledge, so what do we already know, and Carl already walked through quite a bit of what we already know, and identifying the knowledge gaps. To fill those knowledge gaps, we've been conducting both bench, pilot, and full-scale tests, and then we're summarizing all of the results in peer-reviewed publications. And we're focused on peer-reviewed publications, particularly for this project, because we want to be sure that any of the results can be considered for regulatory decision by EPA and state authorities. And so it is critical that they be peer-reviewed. The specific research questions the project is looking at is documenting the efficacy of PAA disinfection for fecal and total coliforms, coli and enterococcus, as well as viruses. Also to look at how does upstream wastewater quality impact how well PAA behaves. So what are the different water quality parameters that really dictate whether it's going to work or not for you? And how does PAA in turn affect the pH, CBOD, and other parameters of the solids, as well as the effluent, final effluent. Carl mentioned that you do see an increase in CBOD, and you also see an improvement in dissolved oxygen, typically, unless you overquench. We're documenting the effects of PAA on aquatic life. Carl touched on wet testing results. We're also compiling all of the wet testing results from our partner utilities and looking at other ways that PAA can be used in wastewater treatment, such as potentially for upstream of filters for filter control. And finally, the research project is looking at decreasing the regulatory ambiguity for PAA, particularly around the residual requirement and monitoring and the testing method that can be used. The project kicked off last September, and we started with a utility workshop in October hosted by Trinity River Authority, and then moved into our pilot demonstration phase with 4 partners in Texas, and continued this year with some more pilot testing around the country, as well as looking at data of UV with PAA. We're analyzing the data and writing our peer-reviewed publications, and we will have a summary of that research next year, as well as a comprehensive guidance document in partnership with WEF. So looking at some of the partners involved, the stars show Texas utilities that are sharing data or have conducted extension pilot tests as part of this research project. You can see that we've conducted a number of extension pilot tests looking at different indicator organisms, as well as cold weather conditions up in Vancouver, and the condition of UV plus PAA in Georgia, Gwinnett County. As I mentioned, Trinity River Authority did a full-scale tertiary filter trial, which is a nice element of this project. We're, as I mentioned, publishing a range of articles looking at the state of the knowledge, the impact on effluent quality, and economics of PAA. We've published 2 papers on virus inactivation, and we will summarize all the toxicity data that we have in an article, as well as an article summarizing what would be needed to be able to achieve an EPA-approved method for monitoring PAA. The other project deliverables will include an economic evaluation tool and spreadsheet tool to evaluate the pros and cons of PAA for your specific context, and a final research report that will be a brief, practical executive summary of the work done in the project, as well as that longer WEF special publication. Looking ahead, we feel that PAA is a viable tool in the toolbox. It supplements existing options. It's not always the right choice, but certainly is worthy of consideration. And this research and other research ongoing at utilities around the country is really driving towards furthering the conversation about PAA and hoping to make the regulatory and permitting processes smoother. Thank you.
Okay, thanks, Dr. De Silva. If everyone can hear me okay, I have a case study that the first case study of our webinar that I wanted to share with everyone this afternoon. As Dr. De Silva mentioned, what we're finding from the research is that PAA can be an effective primary disinfectant for wastewater to meet indicator organism limits, or it can be a successful supplemental disinfectant. And so this first case study is a project in nearby Little Rock, Arkansas, that went from a pilot scale demonstration to a full-scale project now, a full-scale trial with PAA as a supplemental disinfectant to UV. So this particular facility is called Adams Field. It is the largest municipal water reclamation facility in central Arkansas. It's a conventional activated sludge facility with, as you can see from this aerial, with aeration basins, primary clarifiers, aeration basins, secondary clarifiers, and in the back here you see in a small box here the UV disinfection facility. So it's currently a UV disinfection facility that started with UV disinfection in 2008, and prior to that was a primary disinfection with chlorination, gas chlorination. In the background, at the top of the figure here, you see the water body that receives effluent from Adams Field, and that's the Arkansas River in the Mississippi River watershed. So the switch to UV was predicated by more stringent total residual chlorine limits on discharges to the Arkansas River, and so back in 2008, they converted to UV for an average day flow of 36 million gallons per day. The challenges since the conversion to UV I think are similar to what a lot of facilities see, regardless of their disinfectant. This is not necessarily unique to UV, but what we're seeing here in this graph is the effluent fecal coliform historically since 2008 at Adams Field with increasing flow through the plant. And so again, whether it's UV or it's a chemical disinfectant like chlorine, what happens is that as we increase flow through these facilities, it's often the case that we lose residence time or contact time in disinfection facilities and disinfection basins, and we see elevated effluent fecal coliform. But given the peaking factors that for flow that this particular facility receives, it became challenging to consistently meet limits, or became evident that we would be close to seasonal limits with UV without supplemental disinfectant. The other challenge for this particular UV facility is suppressed UVT, and this is quite common for secondary effluent disinfection applications of UV as well. When you see variability in UV transmittance, that affects the penetration of the UV light through the water column, and therefore the amount of light that hits our bugs that we're trying to inactivate, like E. coli or fecal coliform, if those are your indicator organisms. For many facilities that would be designed for secondary effluent, a typical design UVT can be 65%. But when we're looking at historical Adams Field UV transmittance data from their online UV transmittance analyzer, what we see really is a 10th percentile, or if we were to go back in time and relook at UV applications for this facility, it might be designed for something like 55% UVT, or to deliver a minimum UV dose at a much lower UVT. So that was particularly challenging for this facility as well. So in 2014, Little Rock Water Reclamation Authority was at a crossroads. Their first question was to replace or to consider replacing the existing UV. However, it was certainly not anywhere near its useful design life. It had been back in 2014. It was only a 6-year-old system. So there was the idea of supplementing UV with a chemical disinfectant. And again, residual chlorine was a strict residual chlorine limits on effluent discharges was a real concern, and the lack of a contact basin was also a major concern, given that as many facilities do when they retrofit a chlorine facility for UV, they replace the chlorine contact basin with open channel UV systems, and that was the case for Adams Field as well. So there was a lack of a basin to achieve contact with chlorine, and there was also therefore a lack of a suitable place to inject, say, a sulfur dioxide to quench that chlorine before it's discharged to the receiving stream. So with a little bit of a leap of faith, the project moved forward by examining peracetic acid as that potential supplemental disinfectant instead of free or total chlorine residuals. Before we did take that leap of faith, however, there was a pilot study, and I wanted to point that out, that a pilot study was conducted for about 6 weeks in 2015 to assess the dosing requirements in their secondary clarifier effluent, again with the idea that it could assist UV, not replace UV in meeting effluent fecal coliform limits. So the thought all along was, could we keep a stable peracetic acid bulk solution on the shelf, so to speak, for the challenging conditions that we know exist for UV disinfection, high flows, poor UVT, etc. So this pilot what also makes it unique is that it was designed, constructed in a lot of almost entirely by and operated by Little Rock Water Reclamation Authority staff. So you see here in this picture a PVC plug flow reactor that again was constructed by Little Rock Wastewater at Adams Field. It was designed at the top of the figure here to intercept secondary clarifier effluent. So we're pumping out of the secondary effluent clarifier effluent collection box through this PVC reactor with different doses of peracetic acid with multiple sampling points along the way. And it doubles back, as you can see in this figure here, because what we were doing is discharging that PAA treated effluent to a clean out that went back to the head of the plant. So without getting into a lot of the details of the pilot study and the results of the pilot study, I think that for this conversation, there were some key outcomes that affected the full-scale trial, the success of the full-scale trial and the design of that full-scale trial. The first major outcome, which was, again, we keep in mind that we, by replacing the chlorine contact basins with UV, there was not much contact time available for a chemical disinfectant. So we were essentially looking at short runs of conduit between the secondary clarifier effluent collection box and the new or current UV disinfection channels. And so relative CTs, as Dr. Linden pointed out, for PAA were fairly small in terms of what was available at normal flows and peak flows of this plant. So very cool outcomes from this project included that with CTs of 10 milligram minutes per liter of residual PAA times the available contact time, we were seeing final fecal coliform concentrations in the pilot reactor less than 1,000 CFU per 100 mil. So that's less than one of their seasonal limits for the Adams Field Treatment Facility for discharge, just with PAA alone. And so this was not considering the additional disinfection that would come from UV. With a double that relative contact time, or CT, of 20 milligram minutes per liter, we could get down to, again, with just PAA, less than 100 CFU per 100 mil at the end of that pilot reactor. So this was pretty exciting results and led to the next phase of the project, which was a full-scale application. The other positive benefit that may or may not have been mentioned already this morning is that we did see, as Dr. Linden pointed out, we do see as a byproduct of the breakdown of peracetic acid some dissolved oxygen, and that was evident in the pilot study where we were able to measure an increase of about 1-to-1 in terms of parts of DO per part of PAA that was added in effluent DO increase at the end of the pilot reactor. Some side effects that have also been mentioned so far this morning that were evident from the pilot study. We did see at the end of the pilot reactor some pH suppression. This should not be necessarily a surprise for fully nitrified secondary effluents like Adams Field effluent. There's typically low alkalinity, and so when we're adding an acid like peracetic acid, we should expect some pH suppression. And so we did see, on average, about 0.3 pH units drop in pH at the end of the pilot reactor. So that if it was coming in at 6.9, we were seeing typically 6.6 in terms of pH units at the end of the pilot reactor. And again, as this has been pointed out by our previous speakers, we did see some increase in BOD on a 1-to-1 level, parts of PAA to parts BOD increase in the pilot effluent. So this was very encouraging results, I think, overall, and led to a full-scale trial that began in 2016. Here we're showing the temporary utilization of the old chlorine storage building. So if you can see my mouse here and the aerial shot here on the right, that was the old chlorine storage building that we're showing here in the drawings in the back. That was retrofit for bulk storage of 300-gallon totes of 15% peracetic acid product with temporary chemical pumping facilities, as well as some, of course, necessary chemical safety showers and eye washes as well that were brought back online to make sure this project was a success. So that chemical is stored in the back here near the loading dock of the old chlorine building, is now pumped for the full-scale trial, is pumped back to that secondary clarifier effluent collection box. So our PAA contact that's available is a 72-inch reinforced concrete pipe that runs along this blue arrow, which then it is intercepted by the UV influent channel. This is our second blue arrow. And actually, our PAA contact continues through the UV facility. And in this case, without residual quenching, we carry the PAA to some degree out to the Arkansas River. So here's some pictures of that retrofit. Here's the old chlorine storage facility, the loading dock now with containment for bulk tanks, 300-gallon totes of peracetic acid, the IBC containment pallets that are used to contain a spill, if any, from those 300-gallon totes during feed. Peristaltic pumping is provided in this unit here to push that peracetic acid to the secondary clarifier effluent collection box. Here's another picture of the totes loaded up and feeding. There was also some new carrier piping that was constructed by Little Rock Water Reclamation Authority to carry that PAA in semi-rigid PTFE tubing through this PVC carrier line into the secondary clarifier effluent collection box. You'll notice from this picture that there's not necessarily mechanical mixing. This is a part of the trial and error and the valuable lessons that can be learned from trials like this. There was a discussion early on to mechanical mix or to provide some kind of mixing or not. Since it was a trial, we decided to, with Little Rock Wastewater, decided to look at the effects of just going straight from the PTFE tubing into that secondary clarifier effluent collection box, and found that there was quite a bit of success in good chemical dispersion just with that introduction method alone. So we were getting good dissolution of the PAA injected in that secondary clarifier effluent and getting the disinfection we needed. So there hasn't been a retrofit for mechanical mixing in that particular application point. A lot of data is being collected. This full-scale trial is still ongoing. I wanted to point out the dosing parameters. A minimum PAA dose that's been applied since August of 2016 is 0.5 milligrams per liter PAA. The other thing to point out, whenever they're applying PAA, the UV is on as well. So UV is continuously running. And so part of the data set that's being collected is the effect of peracetic acid on the operation of the UV disinfection channel. We're looking at the effect of PAA on the effluent UVT, the number of UV channels that are in operation, how much power is required in those UV channels, given the PAA dose upstream. But going back to the PAA dose, the max PAA dose that's been applied is 1.5, and as Dr. De Silva pointed out, the state of Arkansas has currently set for these kinds of trials a temporary limit of 2 milligrams per liter, and that was the case here for Adams Field, that the final discharge could not exceed 2 milligrams per liter PAA residual to the Arkansas River, and so that kind of set the cap on PAA dosing that Adams Field was comfortable using. And of course, along with the UV operating parameters, there's quite a bit of secondary effluent fecal coliform data, as well as final effluent fecal coliform data that was collected for this project. So I'll dive into some of that to share with you some of the results of this full-scale trial. What we're seeing is that so far over the last year or so of this full-scale trial is that PAA upstream of the UV has assisted Little Rock Water Reclamation Authority in meeting their seasonal effluent coliform limits. So they have a seasonal limit in the cold months of 1,000 CFU per 100 mils. So for this particular graph, we focused on those colder months, which can be a challenge for any disinfection system, especially chemical disinfection systems. And so in those colder water temperatures, what we're seeing, which is quite surprising and very cool for this particular application, is that from the secondary effluent fecal coliform bacteria counts, which are the blue circles or blue dots here, to the coliform counts that were sampled prior to UV disinfection with PAA online, which are the blue open squares, we're seeing that on a log scale, almost 1 to 2 log inactivation of peracetic acid in some cases. Inactivation of fecal coliform with peracetic acid alone on some days. And so overall, though, when we again go down the graph here on the log scale, we see even greater disinfection, as we might expect from the application of PAA in conjunction with UV. So now the final fecal coliform bacteria counts are the orange X's on the bottom. And so in all cases, they were well below their seasonal limits, even though the water quality or water temperature conditions would not necessarily be conducive to high levels of disinfection. To give you a sense of how much additional benefit they're getting with peracetic acid, even though UV is running as well, for the period of August to December of last year, we're looking at effluent fecal coliform bacteria in CFU per 100 mil on the y-axis, first with PAA and UV, so that's our blue square, our blue box and whisker plot, and then our black box and whisker plot is just the fecal bacteria concentrations with UV alone, so without PAA addition. And so the benefit is pretty, the contrast is pretty stark here, that we're seeing on average about 1 log or 90% improvement to reduction in fecal coliform counts in the final effluent through the combination of PAA and UV. It's very cool stuff coming out of this full-scale trial. This approximate 1 log fecal coliform bacteria inactivation is occurring with relatively short PAA contact time. So Given the hydraulics of this plant, and given that there's essentially that RCP pipe that carries secondary effluent to the UV channel, and then the UV channels themselves is all the contact time we have available. When we started to plot the contact time as a function of the flow through the plant versus the initial fecal coliform bacteria counts in that secondary effluent, what you're seeing again is just in very short contact times, significant degradation of fecal coliform bacteria with again low doses of PAA, less than 1 in most cases, milligram per liter dose to that secondary effluent. So it's proven to be in secondary clarifier effluent a valuable tool, as Dr. De Silva mentioned, in the toolkit for inactivation of fecal coliform bacteria. The other cool thing that it's doing, or the other benefit that Little Rock is seeing, is that it's helping to manage fecal coliform bacteria even during unexpected variability in effluent UVT. Here's one particular event. We're looking at a window in time from August 2016 to December of 2016. What we're looking at is the continuous measurement of UVT, effluent UVT at the plant. And so you see that in general on the right, the y-axis on the right, you see that for this blue line, they're typically hovering around 70% UVT, which is excellent for a secondary clarifier effluent. But then right around the end of September, they see some variability, some spikes, and overall a declining trend in UVT. And that could be something in the collection system. It's very difficult to always know what can be happening in your in the wastewater you're receiving at your plant that could affect your UVT if you're running a UV disinfection system. But having PAA on the shelf again as a supplemental disinfectant, they were able to bring that PAA online, and the red dots show how they were able to manage their effluent fecal coliform bacteria. So our y-axis on the left shows they were in all cases during this period below 40 CFU per 100 mil with a combination of PAA and UV. So even when the UVT was dropping to 50, 40, in some cases less than 30% UVT, they were able to manage their fecal coliform bacteria. As Dr. Linden mentioned, the initial rate of PAA decay can be quite slow, and that was evident during pilot testing. So up to about 12 minutes here, we're seeing about a 20% decline in initial PAA at the end of the pilot study that was conducted at Little Rock Wastewater. When we overlay the pilot scale, or I'm sorry, the full scale results, which are now the red dots, what you're seeing is kind of, I guess it could be described as the inverse of what we would typically expect in terms of second order decay of a chemical disinfectant through in a secondary effluent, where we might expect to see some fast initial decline in the chemical disinfectant with slow, with a second lag phase where we see slow decline in that residual. And in this case, given that these are individual dots, are individual snapshots and grab samples at different points in time, when we overlay the two data sets, what we're seeing is that from the secondary clarifier, in terms of the hydraulics of the plant, to the UV, we see some slow decline in PAA, and then through the UV reactor, which is represented by contact times greater than 10 minutes, we're seeing an accelerated rate of decay. So pretty cool stuff in terms of the potential for some enhanced photodegradation of PAA and potentially a benefit for managing residuals that might create some or might have some toxic effects. It's still to be determined in the receiving streams for these water reclamation facilities. So to wrap up, what we're seeing out of this full-scale trial, which again is still ongoing, we're seeing some really cool results in terms of fecal coliform bacteria inactivation due to the PAA alone. So low initial PAA doses of 1 milligram per liter on average, short contact times if we're thinking about just the window, that's PAA disinfection. And PAA is also assisted in maintaining consistent effluent fecal coliform bacteria at the plant, even with fluctuating UVT, which was a significant benefit for this project. And finally, in terms of potential impacts for other facilities, if you're thinking about peracetic acid, I think as our previous two speakers have mentioned, there is some, if you are, say, a type 1 reuse production plant here in Texas, if you have a stringent BOD limit, that could potentially put a cap on the amount of PAA you can use. It doesn't necessarily mean it's not going to be effective at your facility. It just could limit the amount of peracetic acid that you add, given the increase in BOD that can be seen in effluent. So before I turn it over to our last speakers, I wanted to acknowledge the heavy lifters on all of this pilot and full-scale trial data, the staff at Little Rock Water Reclamation Authority, Walter Collins, John Thompson, Joanna Brown, and Eric Wassel at Adams Field Treatment Facility, and then folks in our Little Rock office that have been instrumental in getting this data and getting the pilot and trial off the ground. So Aaron Stallman and Paul Strickland. So with that, I will turn it over to Sarah and Leonard.
Here, we're off mute now. Oh, I'm on the wrong hand. Okay. All right, thank you. Good. All right. So we're going to talk to you today a little bit about a little different project. As soon as we fix it, as soon as the computer decides. Okay. Gulf Coast Authority was founded in 1969 as Gulf Coast Waste Disposal Authority. Initially, we were just around Galveston Bay. We were formed to help clean up Galveston Bay. I just want to point out that's a year before EPA was founded and 3 years before the Clean Water Act. We're completely funded by user fees. We have several different operating facilities. We primarily have regional facilities treating industrial waste, chemical plant waste, refineries, and so on. The facility we're going to talk about today is our Washburn Tunnel facility.
Okay, that's the question.
Okay, I'm sorry. So Washburn Tunnel facility, it's treating primarily refinery waste, though it does have chemical waste, and about 8 to 10% contribution from municipal waste. Why is it not working? Why is it working? Okay, there's two different waste streams that come into this facility. The waste streams that have a large amount of volatile organic compounds go to a first stage oxygen activated sludge plant where the VOCs are destroyed. The streams that without any volatile organics go to the primary clarifier. They combine, they're split between parallel activated sludge systems. And prior to this project, they then combined at the outfall and went to the Houston Ship Channel. One thing you'll notice from this aerial, there was no existing end of pipe disinfection system at the facility. The project was to design and implement a system to meet some bacterial enterococci effluent limits and keep the facility operating during the conversion. We were challenged in a couple areas. The big challenges, we didn't have any footprint. We had very limited amount of hydraulic gradient to work with, and we could not move the discharge outfall at all. Here's the wastewater characteristics. At the time that we did this, it was going to be the largest peracetic acid disinfection system in North America. The key things to look at here that really drove our decision to go to peracetic acid are the very low UV transmittance and the relatively high peaks of nitrite, and we would get some kind of nitrate lock in our nitrification system. We looked at a whole bunch of different alternatives, and for several different factors, we ended up with the chemical dosing is going to really be the ones that we had to focus on, either chlorination and chloramidination, or go ahead and go with peracetic acid. So about 2012 or so, we set up our pilot reactor. We told our maintenance people we want a big long tube with a bunch of different sample points, and this is what they came out with. And it worked really well. We ran the test in parallel, and what we found out, obviously, is that we should go to peracetic acid. And the big drivers were there was a reduced contact time, which resulted in lower capital costs, and capital costs was a huge driver in this facility. And there was a lot less variability, primarily because of the nitrite that was there and not there. We did a lot of CT testing during this pilot study, and what we found out is that 7.5 minutes on peracetic acid was going to work for this waste, and 15 minutes for chlorine. And our design doses are a little bit higher than what you've seen other people say, but that's probably because of the industrial component. Since we were one of the first systems, in fact, we were the first system in the state of Texas to use this, we were a little bit concerned about potential effluent toxicity. So we put in a sodium bisulfite quenching system into the design. After startup, we were going to test to see if we could operate without that and still not have any effluent toxicity issues. However, all of our facilities are permitted as if they are industrial facilities. And that means that they have technology-based limits based on the industries that are discharging to them. One of those industries that we're allowed to receive waste from had a limit that you could not discharge any measurable chlorine. The PAA test measures, shows up as, the chlorine test picks up PAA and shows that as chlorine. So therefore, we had to abandon, and we didn't do that whole idea and just stick with the quenching system. Because of our very limited amount of space that we had to do a lot of work on how to fit it in, did a lot of value engineering, and a lot of hydraulic work, and we spent a lot of time on PAA procurement. What we decided to do is that in order to minimize capital, we were going to bid the peracetic acid as feed equipment as part of the PAA chemical supply contract. Probably one of the biggest challenges we had was how are we going to take these two different discharges that mix into that outfall box and put them through a single disinfection system, get that back in with very little head. On top of that, we had to make sure that we could fill these trucks full of sludge from this sludge dewatering operation, not only throughout the construction, but also throughout after we start up. So we couldn't build anything that was going to interfere with that flow. So we came up with what we think are some pretty brilliant solutions on that, counterintuitive. We basically made water flow uphill through our gravity lines, and we went through, as you can see, our new PAA disinfection system. And then in order to get it to go out of the outfall, we actually had to install a wall inside the existing effluent box, push the water uphill, come back in, install a new box at the end, come back in, and then out the outfalls. And believe it or not, this was the absolute simplest design that we could come up with. And yes, it was one of our Aggie engineers that came up with it. But because of all this, we had to come up with an asymmetrical contact chamber design. In terms of permitting, we had done prior work to this, and our permit, we do not have to meet the domestic design criteria because it's an industrial treatment facility. So we actually got written into our permit the flexibility of going either with the chlorine system or with the Paracetic acid system. I'm going to turn it over to Sarah now. Just remember, just don't use these. Use the scroll bar.
Okay. So
Try that. Okay. Use the scroll bar.
Okay. So as you can see here, we have the asymmetrical design. So we have an outer and inner channel where the water comes in on the side. Basically, this allowed for a very tight footprint. The Peracetic acid and sodium bisulfite storage areas there next to the partial flume are contact areas, part of the flow measurement. In order to verify that we were still getting an even flow split and appropriate mixing, we did two variations on the CFD modeling. One was for the flow split between the two channels, make sure that it was within a level of accuracy as we were using the partial flume to handle the effluent levels. And then second, for mixing systems, to make sure we're getting adequate distribution of PAA. Because we have such a short contact time in the design, the rapid dispersal of Paracetic acid is very important to maximize the effectiveness of it. So you can see here, we actually determined that during design, we needed to add a baffle plate in one of the two mixing chambers to help with the flow split during low flows to keep that as even as possible. Another thing we had to develop, and some of this is the timing. When we did this project, there was only one other facility we knew of in the U.S. using Paracetic acid. I mean, we started well ahead of a lot of the research and things at this point. So we started this PAA procurement documents basically from scratch, interviewing PAA vendors, determining scopes of work, in terms of what did we want from them, what were their standards. I mean, we were ahead of what standard systems were even available. Like this is an 001 production model. We did get through, and as Leonard mentioned, we leased the equipment and then negotiated a long-term chemical purchase contract. We also included system maintenance on the overall Paracetic acid, but system operations still being performed by the plant staff. So through construction startup, another unique thing is that we were under a bit of a schedule driver for this project. By our permit, we needed to be up and running by January 16. So this was constructed as a design CMAR, so construction manager at risk that CDM constructors built. A few things to note here is we did get through the project with perfect safety records, so 29,502 employee hours without injury or illness involving days away from work, so we're very proud of that. The box that Leonard had showed in one of the previous slides, this is a photo looking down it, that wall is 40 feet high. So we could have 35 feet of water on one side and 2 on the opposite. So that's just to construct it, to build it, to design it. We were 2 years in maintenance of plant operations, safety for construction, 2 years in planning just for this one temporary effluent outfall. So it was 6 weeks in construction, and we were able to get this constructed with no interruption of service to the industries, which was a large driver for us in this. Here's a few photos of the construction. You can see how close to Houston shipping channels we are. Some of the large oversized pipes, we were able to construct it in 14 months on time. And of course, happy to say we were also on budget. Another unique item that we did after construction is that we did do an extended 6-month startup period. So we looked at sampling not only just what's in and out of the basin, but what was going on throughout the basin. What we found is that there were some interferences with some of the water quality parameters in the Taro, and that optimization of the dose. On this chart, you can see our original design doses were selected at 3.5 at a peak of 8. that dose goes up as the flow rate goes up in the facility to maintain the CT. Our optimized doses we were able to lower by half a part on our average day, and then down to 5.5 a peak. That resulted in about $100,000 per year savings. One other thing we'll note is that with this 3.5 parts, you know, our typical effluent is less than 1, typically more like half a part at the end of the tank, and that's at 20 minutes. So we do see a much more rapid PAA decay than what some of the other papers or panels have presented today. So there's certainly some variability here. And wrapping up, you know, lessons learned for us is that, you know, PAA did provide a cost-effective pathogen control for the facility. You know, selection of PAA provider prior to construction was very crucial in getting this done. You know, coordination works. We were meeting early and often with the Peracetic acid supplier, the contractors, the plant personnel and operators, the GCA project development team, really throughout the whole process, starting from the value engineering session, our Aggie design on the effluent box, and really even just through startup and planning and commissioning. So that was very crucial to this. Again, that really helped us to, you know, address and make sure that we were handling facility operational issues early. One thing we included was covering the basins. At that time, we had been told that algae growth was something people had seen previously. So we did cover the basins, and we have not seen algae growth, but we have seen a buildup of scum collection over time. The one thing we had it all to do over again. We should have added scum and a way to get it out. Yep. The CSE modeling proved to be very useful with the asymmetrical basin design, so that was good. And that optimization after startup, the cost in doing that extra sampling was paid for very rapidly into cost savings for peracetic acid. Finally, keep in mind that PAA measures with chlorine on your testing, so that did impact, you know, our need for long-term quenching. And we did find that with our high temperatures, the water can get as high as 105 degrees in the effluent leaving the plant, that it was interfering with some of our online instruments measuring the peracetic acid. So with that, we'd like to definitely acknowledge Leonard and the GCA staff, Joanne and Carl, many, many others, team of people with CDM Smith, both on the construction design side, Proxy Chems, who supplied peracetic acid to an area that you can see, and finally Stantec with Keeney Bell, who's very helpful us early in the project in helping select the technology. So with that, we'll turn it back over to Julie.
Okay, yeah, I think I'll pick it up. I think we have about 15 minutes left, which is perfect timing for Q&A. And a couple of questions have come in. Continue to fire off your questions if you have them for the remaining minutes here. First question, I think I'm going to send this to you, LRWRA. As you mentioned, that there are some alternative approaches for measuring PAA residuals. This question states, if you need to have a residual, what test are you doing to measure? Is it wet chemistry or is it amperometric?
Sure, thanks for the question. Yes, it's very similar to chlorine. You can use both the DPD wet chemistry kits where you take a grab sample and there's ampules and it's a colorimetric test, or you can also use amperometric probes and even DPD-based probes that are inline probes to have real-time monitoring.
Okay, our second question is regarding the facility in Arkansas. Why wasn't tertiary treatment considered prior to UV? Shouldn't that have helped? Great question. I think tertiary treatment would definitely have helped in terms of reducing the fecal coliform bacteria load on the UV, and I think that facilities that use tertiary filters in front of UV do see that benefit. When thinking about supplemental disinfection as an alternative, it certainly is an attractive alternative when we think about PAA in front of the UV, because it is for facilities that are struggling now with high fecal coliform bacteria loads, it's a way to quickly develop a solution for those fecal coliform bacteria in a cost-effective manner that goes in pretty quickly. So I think it's from a long-term perspective, tertiary treatment makes a lot of sense in front of UV, but when we're thinking about the role of alternative technologies like peracetic acid, they may be as a stopgap of sorts before tertiary treatment is implemented. So I hope that answers question number 2. And let's see, do we have any more coming in? Question 3. Okay. So for the GCWA plant, were any studies done of the built structure to confirm that the results of the CFD model were actually correct?
Yeah, we'll answer that. Actually, no. And our new name is GCA. The legislature decided that the last session. So we're just Gulf Coast Authority now. But no, we didn't do that. We didn't see any value in that. We kind of didn't want to get into a pure research mode on this project.
I would add that the way the design's set up, each channel can operate independently, so that it can run either on the inner or outer channel, so it's got its own dedicated feed pumps, controls, and everything else. So if needed, they could, alternate dose and flow rates by channel. So we provided that flexibility in the design initially, but at this point, it's not proven necessary.
Right, and in actual practice, since we do have the 2 channels, we often only operate on one channel, and it's just really flow rate driven. Because if the flow rate gets above a certain amount, we'll open the new channel, and that keeps our contact time down to less than 15, 10 to 15 minutes on a normal flow.
Okay, and we still have time, folks, if you want to send in some more questions. I do want to, I'm being told to point out, though, that we do have CEU questions. So in order to receive credit, TCQ credit or CEU credit or PDH credit, these questions have to be answered, and they're based on the material that was shared today in today's webinar. Question 1 is, peracetic acid is an effective disinfectant for E. coli. It's a true or false question. 2, which of the following is the driver for the use of peracetic acid for disinfection? It's safer than chlorine, it's more stable than liquid chlorine, no disinfection byproducts, or D, all of the above. And the final question, a dose of 1 milligram per liter of peracetic acid will approximately add 1 milligram per liter of BOD to the effluent, and that's a true or false question as well. Please complete these questions, submit them to Melissa at WEAT.org. Also, if you're seeking credit, you should visit this the URL at the bottom of the screen, www.wheat.org/peracetic acid webinar.shtml.
And just to clarify for everyone watching the webinar, Mike, will you go through those questions again, answer them, please? And
so I give away the answers?
Yes, give them the answers. Okay. And as he said, operators, if you are seeking credit, please answer these found on the question sheet at wheat.org/peracetic acid webinar.shtml, or answer them in the follow-up questionnaire poll survey that will be sent out by GoToWebinar. Thanks.
Okay, so let's go back to 1. Peracetic acid is an effective disinfectant for E. coli. That would be true. The evidence we saw today is that it is an effective disinfectant for E. coli. 2, which of the following is the driver for the use of peracetic acid for disinfection? Safer than chlorine, more stable than liquid chlorine, no disinfection byproducts. In fact, the answer is D, all of the above. So 1A, 2D, as in dog, and 3, a dose of 1 milligram per liter of peracetic acid will approximately add 1 milligram per liter of BOD to the effluent. That's true. So 3 is A. So it's 1A, 2D as in dog, and 3A. So submit those to Melissa at wheat.org.
Since there's no more questions, we'd like to add something. Something Sarah and I noticed on this is that if you look through the data, and from the data that we've seen presented from other sites, it looks quite a bit different from the data on our site. So if anybody's contemplating doing this, we really urge you to do site-specific testing on your site, and then make a determination what type of disinfection system is going to be right for you.
Excellent point, Leonard. Yeah, I think that should also be a key outcome from this, is to do some kind of initial screening of your water with peracetic acid, and that could be as simple as some initial laboratory bench tests. We are also getting so a couple more questions are coming in. Question 4. Let's see. This is a follow-up, I think, for LRWRA. Are the DPD methods and probes sold, marketed for chlorine?
So there's some dedicated probes that are labeled for PAA. The method for measurement is the same as for chlorine, so you can use chlorine probes as well and use correction factors for PAA. But again, there are probes specifically labeled for PAA, so that correction factor is already factored in. And then the DPD kits, there are some on the market from WRRF that are specifically marketed for PAA, so those are available.
Okay, and then there's another question that came in. This might be for the entire panel here. With the reduced effectiveness against viruses, I think that's a PAA against viruses. Is there discussion of TCQ changing the indicator organism?
And Mike, this is Carl, and I'd like to just mention something there as well. There aren't a lot of data actually on many different viruses and disinfection of viruses with PAA. So I think that's an area of research that we need to think about beefing up. Certainly we know the indicator organisms are disinfected, but I think it's a really good point the questioner makes. Considering the lower efficacy against some viruses, as well as some spores and a likely Cryptosporidium and Giardia by PAA, to what extent might there be a better indicator organism? But certainly, for regulatory compliance, we know we can meet that, but that might not answer all the questions. I think there's still some more research needs to get done in that area of pathogen inactivation in wastewater.
Any other thoughts on that on the panel?
I know from Gulf Coast standpoint, we don't know of any move by the agency to come to do anything like that.
Yeah.
In Texas.
I mean, it sounds like the state agencies, not just TCQ in general, they're kind of waiting to see what EPA is going to publish next year in terms of draft criteria, numeric criteria for virus and recreational waters. So it's kind of a wait and see game, I think. And as Carl pointed out, there's still a lot to learn about how a PAA interacts with viruses of different natures and types. So it's a stay tuned, I guess, is the best answer for that particular question.
Mike, I know if anyone attended West Tech last week, there were some papers given on virus effectiveness with peracetic acid on some current studies. So if you have access to those, there are some publications that are pretty recent on that.
This is LRWRA. I mentioned on one of our slides we have 2 publications looking at MS2 bacteriophage and mouse norovirus. And this was just on one wastewater. So this was in Denver's main wastewater treatment plant, Denver Metro. In that wastewater, PAA was shown to be similarly effective at inactivation of MS2 compared to monochloramine. So we didn't see a problem with virus disinfection if MS2 bacteriophage were the EPA recommended viral surrogate. We saw a little different results from mouse norovirus, which is a surrogate for human norovirus, that it seemed to be more susceptible to monochloramine and less susceptible to PAA. So I think we'll, like the other speakers have said, we'll need to dig into this a bit more, but it does depend which virus you're looking at, and maybe even specifically the wastewater. So it certainly is complex. But just to underscore that, we didn't see a problem with virus inactivation in the Denver wastewater study.
Okay, we've got one more minute, and we've got a couple questions, so we'll see if we can get to these both, and then I think we'll call it a webinar. So question 8, is any domestic-only facility in Texas currently in trial? Would EPA approval be needed, and what remaining hurdles would there be? For example, possible toxicity, approved testing method? I think, I mean, if I was going to take a first crack at that, I think that the answer is that there are Texas facilities that have trialed peracetic acid to some varying success, and I think we'll be hearing more about those results at great events, WEAT events like Texas Water next year. Would EPA approval be needed? I think what we're hearing from these case studies presented today is it really comes down to a good, frank conversation between the utility and the state. In the Little Rock example, the success of that project was predicated by open dialogue and data sharing between that utility and the state agency, and in fact, the EPA was not involved in that. And I think in the Gulf Coast example, we heard something similar, although I'll let Leonard and Sarah jump in on that. And then what remaining, go ahead.
Yeah, in Texas has delegation for the whole program. So in Texas, you'd be dealing with TCEQ. Can't speak for other states. I can think I would imagine though it has to do with whether they have full delegation or not.
When we trialed in Tennessee, it was just working with the state legislative body. So. Yeah.
And then real quickly, because we're over time here, I think the last question is: are there any studies done showing the effects of PAA on cloth media filters? And the answer is yes, and then we'll call it no. So there are studies being done. I think those are ongoing, and maybe LRWRA, you might have some more background on that as well. But from what I understand is that the cloth media manufacturers are looking at it, as well as specific utilities and potentially some of the foundations. Any other thoughts on that before we go?
Given that we're over, I'd just say yes. I'd echo that and say reach out to me for more, or Matt Jalbert, Trinity River Authority.
Real quick, I want to point something out: is that the Gulf Coast does not have any monitoring requirements on peracetic acid. Our only monitoring requirement is on total chlorine because of the type of industries we're permitted to accept. So we don't ever test our effluent for peracetic acid. We test it for residual chlorine. And the peracetic acid shows up as residual chlorine if you don't quench it.
Okay, and I think, Leonard, yeah, sorry, that answered question 11 about testing methods, and I appreciate you doing that. And I think with that, we're going to call it a day. And thanks to everyone for joining us, and thanks to our speakers. This was a lot of fun, and I hope you enjoy the rest of your afternoon.